All right, hello everyone. Welcome to our next lesson in probability. This topic is a topic I think that doesn't get talked about nearly enough in probability lessons, at least at the high school level. But is super important, I think, because it's something that you see everywhere in life. Um, and, you know, far be it from me to um, glorify gambling or casinos or any of the probabilities associated with that. Certainly, I will be the first person to um, say that, really take a look at all the risks before you engage in such activities. However, we can't escape the fact that the notion of betting odds and their connection to probability is certainly something that you'll see a lot of. We're talking about when you see something, oh, it has 5 to 1 odds or 7 to 3 odds, and what that means and how to interpret that probability as something that is likely, unlikely, and what decision you can make when you see something that's stated like that. Um, Most of the time in classes, we focus on just what traditional probability is. Um, so, from before, uh, from our very first lesson, we know that probability is defined as a ratio of successes out of a whole space. And so the traditional definition here, I'll write in red, probability of an event is equal to success out of total. Okay. Um, but one thing that is also important here is what to do with failures. And yes, we know that, if you don't succeed, we'll consider that a failure. We won't consider ties, anything like that here. And we do know that, you know, success plus fail equals total, right? We do know that equals total. Okay. Um, so again, let's think about a fair coin, right? So we know that the probability of heads is 1/2. But what does that mean? That means that in the long run, or on average, we're going to get approximately the same amount of heads as we do tails. And so, on average, for every one head that we get, we will get one tail, regardless of whether you think of it as success or failure, which one is which. You will get proportionally equal. Now, will the amounts be equal? No. Like, but if you think about it, and one of the things that we looked at last unit is if you had um, so 6 heads and 4 tails, you know, that is a potential that could happen, and that's 60% heads. Um, and despite the fact that they're 2 units apart. Um, so Amazon. So um, but if you were to say flip it 100 times, maybe you'll get, 53 heads and 47 tails. And that's 6 units apart. Instead of being two amounts apart, and now they're 6 units apart. And despite the fact that they're further apart numerically from one another, heads is a much closer 53%, which is closer to the true probability. And you could do this, up to 1,000. You could have 527 heads and 463 or 473 tails. Anything like that. And you could have those numbers get further and further apart, but the ratios get closer and closer together. Okay, but that's something that we know from the previous unit. Okay, um, what is important here is the heads, successes, and the failures, heads and tails, are proportionally about equal. And odds are based on that. So we would actually say in this particular case, the odds are going to be 1 to 1. And so we'll talk about what that means over the next few slides, okay? Okay, now here's the thing though, not everything in life is 50-50, right? Take for example, two players are playing chess in the park. Player A is ranked higher than player B and will win about 60% of the time. Now that's all wonderful because chess has all these different rankings, right? You could be a grandmaster, you could be a novice, and there's all these different skill levels that are all in between. So this is not that hard to conceive. What is this as a probability statement? We might say something along the lines that P of A is equal to 6 out of 10. You might call this, reduce this 3 out of 5. They're going to win 3 out of 5 games. You could say 60%. You could say 0.6. Any of those numbers certainly work. The fractions are especially useful when you know how many games they're going to play, right? Whether they play 5 games where A wins 3, or 10 games and A wins 6 of them. Now, these players, though, when you see these games, these might happen in New York City, Philadelphia, big cities like that, where they have big parks and they have chessboards in the park, and people love to play, right? And they're very competitive at it. And for some people, if you're good at chess, this can be a decent side hustle. So players, many times they will play for money. So let's assume that these two players, player A and player B, they put up $5 per game and they play 10 games. So whoever wins gets $5 from their opponent, essentially. So they put $5 on the table each, and the winner gets all $10. And, winner is, in chess, you have a checkmate. Or oftentimes, especially with skilled players, they tend not to waste motions. And so as soon as they realize that they're in an unwinnable situation, they'll just concede the game. And, that's it. So oftentimes that will happen. Rare times there are stalemates. We'll say here that stalemates just not going to exist. Okay. What do you expect to happen? So player A and player B, right? So player B will win 40% of the time. So what do you expect happens? Well, let's see. Player A will win 6 times. Now, on average, right? Does player A have to win 6 times? No, but we're pretty certain that they're going to win around 6 times. So we'll assume that that's the going average, right? And then B will win 4 times. Okay. So how much money do they end up with? Well, let's see. Let's start with this. Player A, they win 6 times. They win $10 each time, right? Now, yes, some of that money is their own money. We do understand that, but we'll figure that in a bit. So they win 6 times, so they win $60. B wins 4 times, and they win $40. Because when A loses, he loses his money. This is the amount of money that they end up with at the end. A ends up with $60, B ends up with $40 on average. Now, if you take away the fact that they bet 10 times 5 or $60, or sorry, $50, you could, as profit, you could say that A makes a profit of $10 and B has a loss of $10. So in this particular situation, A is a more skilled player, so they're going to win. And they're going to win, they're going to get money. Right? I mean, that only seems fair. really, what is fair? Is fair that people are getting paid according to their skill level? Hmm. So, but here's the issue. Player B knows he's outmatched. Why would he play? Why would he specifically play against a better player for money? Maybe to challenge himself? I guess so. Or maybe to know he knows that money's on the line. Maybe he knows he'll play better. Or maybe he thinks he has an answer to player A. In all of those situations, though, what's happening is player B is pushing up his chance to success. If he feels that he's going to do better, then his probability of winning is not 40%. It's higher than that. Or at least it's what he believes. Contrary to what you may think, there are very few people that would play an unfair game on purpose. Because, especially in the case of, losing money like this, right? The only situation where people knowingly play an unfair game is when you go to a casino. You know the games are designed for the casino to make money, but you're still going to go. Maybe you think you're going to get lucky. Here, maybe player B knows he's going to be lucky. But the issue with that, though, is, player B should have some incentive to gain. And then again, if you think about it, shouldn't player A as well? Yeah, they're a better player to begin with, but shouldn't the purpose be to always strive to be better? And shouldn't player A also have the opportunity to earn money if they play better than they usually do? So it might be better for this to be a fair game. So what we want to do is we want to change how much they put down each game. So they wager an amount that's relative to their skill level. And the idea there is if they do that, then player A is, a better player. So he can afford to risk more. He puts down more money because he is less likely to lose it. Player B is more likely um, to lose money or less likely to win, so maybe he won't bet so much. And the question is there a point where there's an equilibrium? Okay, so in other words, fair. What we're going to define as fair is that the average outcome is a sum of zero. And by a sum of zero, what we're referring to is that for any particular player, their profit, and I'll say this, so I'll highlight this here. So in other words, the profit, so expected profit equals zero for all players. And the idea behind that is, that way if the expected profit is zero, then that's the average. And you could equally likely go in either direction. Equally, if A plays better, then they'll make a little profit. And if B plays better, then they'll make a little profit. So, but the thing is, B just has to play better. They don't have to play significantly better. Like in the original formulation, when you had 5 and 5, B was going to win only 4 games. In order for B to make any money, they would have to figure out a way to win not just one, but 2 extra games. They win 1 game, they break even. And because then it'd be 5 wins, 5 losses. They'd have to win 2 games in order to make a profit. Here, if we can find this point, then they only have to win 1 game to make a profit. So what has to happen? how much does player A have to bet and B have to bet in order to make it a fair game? So let's think about one player at a time, right? So let's say A, since we're focusing on player A. Again, their odds of winning haven't changed, right? So we're going to say that they win 6 and lose 4. Okay, so what should happen is they should win the amount that they win in their wins, and the amount that they lose when they lose should be the same. So what if maybe since they win 6 and 4, right? What if player A bets, let's say, if they bet when they win 6. So let's say maybe when they win $4 from their opponent. And when they lose 6. So the idea being that every time they win, because they win 6 times, they win $4. But every time they lose $6. And I just reverse the numbers to make that happen. And that just works, right? So if they win the 6 games that they win $24. And the 4 that they lose $6 per game. They lose 24, and the net result is 0. So if player A bets $6 and player B bets $4, or any ratio thereof, you could do 3 and 2, or 9 and 6, or whatever else. Um, then player A and B have an equal chance of making a profit. Then in that case, you can just flip this around for B. And if all of a sudden A gives one up, right? And let's say they go 5 and 5. So I'll change color and I'll illustrate this. So what if they instead went 5 and 5? Now all of a sudden they've won 20, but they've lost 30, and now they're $10 behind. So it's an incentive not just for B, but for A to keep playing as best as possible. Okay, so a fair game ends up being the most competitive as well, and generally is the best because in the original formulation, if A is already expected to make a profit, why should they exert themselves? Okay, so this result here, the difference in the amount that they bet, that becomes the odds of the game. So what is that as a definition? The odds against an outcome are given as the number of failures to the number of successes. You might also see this written as, instead of a colon, you could see a colon, or you could see it as um, failures to successes. Some situations you might see the odds for an outcome in which these numbers are reversed. Um, but that would be awfully confusing to have both of them, right? And the difference, of course, being the odds against versus odds for. Um, so, as you can imagine, pretty quickly this became confusing to have both of these. So, one of them had to really kind of take precedence, and odds against is the one that takes precedence. And you'll see why a bit later on. Um, but so the odds against, you write down the number of failures and the number of successes. And what that helps you do is to see like how to balance um, the win rate with the loss rate in order to create a fair bet. Okay, so in this situation, in 10 games, player A wins 6 and loses 4. His odds are 4 to 6. Now, this is considered odds against, but because it's now standardized in 99.99% of situations to use odds against, we just call it odds. And his odds are 4 to 6. And yes, ratios simplify the way that fractions do, so we'll see this as 2 to 3. So you might see it written as 4 to 6. 4 to 6 is another way to write it. You could see that as well. Okay. Odds are used in casinos to set how much two players in a bet should contribute. Um, whether it's two players or whether it's the player in the house, whichever. Um, but what this also means is this gives you an idea of who contributes. So for his odds against, so that means that player B will contribute $4 and player A will contribute $6. And so the reason that it becomes B is, again, the odds against are fails to successes. And what's considered a fail for player A? Player A fails when B wins. And when B wins, that means B should bet $4. And so that's kind of how it works. So likewise, you can say that player B's odds in this game were 6 to 4 because they'll fail 6 times before winning 4 times. Okay, so odds are used casinos to set how much two players in a bet can contribute. But that opens up a whole different can of worms because remember, casinos use these, while they use them, they make sure that they're not fair because, again, casinos have to remain in business, right? If all the bets are perfectly fair in a casino would actually not really stay in business. Um, and that's unfortunate. Well, not unfortunate, I should say, but um, you might think that's surprising a little bit because of all the other ways that casinos can make money. But that's actually true. Okay, let's look at a roulette wheel. In a casino, a roulette wheel has 36 spaces numbered 1 to 36. There are 18 red numbers and 18 black numbers spread evenly across odd and even numbers. We make a bet on 14. What are the odds of winning? Okay, well, let's find the probability, right? So the probability of 14. Now let's see, there's 36 spaces numbered 1 to 36. So given that, it's 1 out of 36, which is, then we look at what odds are. Okay, so what is that as odds? So if you think about it, let's say you spin 36 times. If you spin 36 times, um, and I chose 36 because the denominator here is 36, on average, what's going to happen? Well, let's see. It's on average, we can expect each number is an equal probability, so each number is going to get landed on once. And so only one number is a 14. So you would expect it might land on 14 once, on average, once in the 36 trials, but all the other ones are going to lose. So you're going to win once, but you're going to lose 35 times. And so the failures come first. 35 to 1 odds. And it's no coincidence that this number is one less than 36 because there's one chance to win and everything else is a failure. So that becomes 35 to 1 odds. Okay. Now, what happens if you make bets on groups of numbers, right? Um, so what happens if you make a bet? So you can make a single bet that covers the numbers 1 through 6. And so the way that works is there's a specific spot on the table that you can put your money down, and you say, you know, I'll call it a win if the ball lands on any number from 1 through 6. So what's the probability of that happening? So remember, this counts as a single bet, not as 6 bets, right? So 6 over 36. Now, does that reduce? Yes, that reduces, but we'll talk about that in a second. So if we leave it as 1 over 36, 6 over 36, okay, how many times you win? Again, you do this 36 times. You're going to win 6 times, but you're going to fail 30 times because the remainder of the times outside of the 6. So the odds are 30 to 6. What happens if you reduce it to 1/6? Well, same thing, right? Let's say you play 6 games. Well, in 6 games, you're going to win once. So you'll win approximately once every 6 times that you play. So win 1, fail 5, 5 to 1. And 30 over 6 reduces to 5 over 1. So you can play with these in either reduced form or unreduced form, depending on how you want to think about the problem. So it turns out that the odds they set on this, they set 5 to 1. And so they tend to, like, especially casinos, they'll always reduce them so that it's something out of 1. And what that becomes is how, like, the ratio for every time that you win, how often are you going to fail? Okay. But the most important part of this is then what makes that a fair bet. So let's say the odds are 5 to 1. Then what would be a fair bet? Because you lose 5 and you win 1, what makes that fair? Well, to make that fair, you would have to lose $1 every time you lose so that you can win 5 when you do win. That's what would make it fair. So what ends up happening is that this odds of failed success also then becomes the amount that you can potentially, what you bet versus what the house will bet. So when the bet happens in a fair system, then the what will happen is the house will put up $1, or sorry, they'll put up, I did this backwards. So I apologize here. Not your bet, house bet. I have it backwards. It's the house bet versus your bet. Um, so it's what you stand to win. So house bet. And the reason why it's a house bet first is because this is where you fail. If you fail, then that's the house winning. So the house will put up $5. Why? Because they're going to win much more often. So they'll put up $5 and you'll put up $1 or any multiple thereof. So every time you win, you'll make a profit of $5 because that's what the house put down. Okay. and then this 1 becomes what you bet. So you lose your bet every time that you win, and you win the house bet every time you win. So these two are technically interchangeable. They're two of the same definitions. Now, in a fair game, these will be equal. But as we know, casinos are not always fair. Okay, so for a single number such as 14, the odds are 35 to 1. The casino will pay you $35 if you win, and then you will pay them $1 if you lose. So for 14, same idea, right? So probability of 14, the odds are 35 to 1. And like we said before, this is house bet to your bet. And that's what it would be. It was a fair. And that's actually is what they pay you. However, as I said, casinos are not always fair. On a roulette wheel, in addition to all the other numbers, there are two green numbers, 0 and 00, on the wheel as well. Um, the purpose of those two is they're considered the house advantage. If the wheel were to actually land on 0 and 00, obviously it's going to. There are spots on the wheel, and it does every so often. Um, most bets will lose. And the only time, like, you can bet on those spaces. You can bet on 0, you can bet on 00, um, but most people don't. I mean, you can if you want to, if you think it's overdue to land on them. You're certainly more than welcome to bet on them. Um, but most bets that people make, red versus black, or odds versus even, or group of numbers, zeros are never part of that. So all those bets always lose. And that's how the roulette table makes a little bit of money so that it can operate. So how does that change though? So the probability of a 14 is now no longer 1 out of 36. It's 1 over 38 because of the two green spots. But you are still only paid at 35 to 1. So the true odds, and so we call this true odds, are 37 to 1. Those are your actual legitimate odds of landing on the number 14. But the casino will only pay you at 35 to 1. These are called payout odds. And so the one thing that you're going to realize here is that the $35 is not enough to overcome the 37 times that you actually lose. So if you were to play, say, 38 games, you're going to win once and you're going to lose 37 times. But in those 37 losses, you're going to lose $1. The one time that you do win, you're only going to make back 35. So you're short $2. Um, to extend that thinking, what if we look at 150 games? Okay. So over 150 games, you bet on 14. At 38 to 1, 150 divided by 38 is approximately 4. So you're going to win approximately 4 times. So let's just call it 4. And therefore, you'll have 146 losses. For those 4 wins, you're going to get paid $35 each. For the 146 losses, you lose $1 each. And we're doing this in groups of $1, but it's multiplied by whatever bet you make, right? Okay, so for those 146 losses, of course, you're going to lose $146. For the 4 times that you do win, 35 times 4 is 140. So you've lost $6 in total. That's not bad. Maybe that's the price of entertainment? Perhaps so. Just remember, folks, this only holds if you have the money to make it this far. So in order to play 150 games, literally anything can happen. You could win a few times in a row. You could lose a ton of money in the middle. You just have to make sure that you keep having the money to make these bets. So essentially that means you should have, at least $150 to do this, right? If you're making $1 bets each time. Because you could potentially lose all $150. You could never win. Or you could win a bunch. But in the long run, if you play 150 and then stop, you'll have lost $6 of your 150. That's not bad. That's not bad at all. That's what, 4%? So the game isn't terribly unfair. Not as unfair as some people think. Okay, that's how when odds and fair and unfair get calculated. Now, casino games are great because probabilities are very static. The games play themselves, and like the probability of rolling a 14 doesn't change. The probability of getting a result on dice, like when you play craps, like those are not going to change. Sure, a player rolls the dice or dealer spins the wheel or whatever, but in the end of the day, all that comes out fair. The probability never changes. For some events, though, that we bet on, probabilities do change. That's where we get into things like sports betting. We'll get to that in a second. All right. So, converting to and from odds, given an event with probability E, odds against are 1 minus P over E compared to P of E. And that can be simplified, turned into whole numbers. So this is, 1 minus P of E is what calculates the probability of failure versus the probability of success. If you're given an event, E with odds A against B, you can find the probability from that by using this formula. So for example, if you have odds of, say, 7 to 4, then the probability of success is equal to 4 over 11, which is 36%. That then becomes important to kind of decide what is fair and what isn't. So we're going to look at a couple situations where, we may want to compare odds to probability to see whether a bet is fair or not. Okay. All right. So let's look at this. In a standard deck of cards, 52 cards, right? Odds against drawing a 5. So here's a couple examples, right? How many 5s are there in a deck of cards? Well, let's see, 4, right? So probability of 5 is equal to 4 out of 52. Now you can reduce that to 1 over 13. It's fine. We choose not to. 4 successes, 48 failures, because there are 48 cards in the deck that are not a 5, right? So the odds are 48 to 4 which is equal to 12 to 1. If you reduce this to 1 over 13, you get the 12 to 1 right away, right? 12 failures, 1 success. What about odds against drawing an even number? Well, how many even numbers are there in the deck? 2, 4, 6, 8, 10. Queen? Queen is not a number. Queen is not a number. So we're just going to do 2, 4, 6, 8, 10. There's 4 of each number, right? 20 cards. So there are 20 cards that are even. 20 out of 52. So the odds are going to be 32 to 20. Because there are 32 not even cards and 20 even cards. Does this reduce? Same thing, it just reduced to what, 5 over 13? Which reduces to 8 to 5. So 8 to 5, because there's 8 in any one particular group of 13 cards, you're going to have 8 that are not even and 5 that are even. So that's kind of how odds work. And now what we want to look at is the connection between this and fairness. Okay, so a good example of that is involving horse racing. But this also applies, especially now, at least, especially in the state of Connecticut, where you now have sports betting. Vegas does this too, but like any time that you bet on performance elements, you bet on a football game, you bet on horse racing. I like to think horse racing because this is, at least this has been legal for a lot longer than everything else has. Okay. So the thing is, House will set the odds and they'll set how much they're willing to pay out for a horse race. And they'll say, okay, for the next race coming up, we will pay 7 to 1 on a particular horse. We'll put up $7 against your $1. Because that's what they believe is a fair bet for them. But what do they know? They're not the ones actually racing the horse. You have the horse. The horse could behave differently on different days. There's trainers, there's jockeys, there's all sorts of other elements that could affect how that horse does. So their numbers that the house comes up with at the track, you know, are, I mean, not arbitrary, but they aren't necessarily unfair. And if you know a ton of extra information about the horse, the trainer, the jockey, and you're able to pick out that a horse might be prepared to have a decent day, then it is potentially true that that could become a smart bet. That that could actually be unfair, but unfair in your favor. So here's a good example of that. Suppose there's a horse that has listed in the sheets a payout odds of 7 to 2. So that means, so remember what that means. That means that um, you'll bet. So for your bet of $2, you could potentially win $7. So win $7 on a $2 bet. Now you do your research and you figure that the horse is probably about a 25 chance to win. Um, and you get that based on maybe there's like 4 horses that you think have a legitimate shot at winning. And this is one of them. Maybe something like that, right? There's lots of information that they study, that people who are really big into horse racing, that they study. Um, Mind you, this is, by the way, the fact that we're doing this problem, I should point out now, is not a endorsement at all of horse racing. Always make sure that we are treating our animal friends as best as possible. So hopefully that you know, this racing as a sport is done in a safe and humane way. Okay, um, so we're doing research here, and the horse has a 25% chance of winning. So really what you're doing is you're comparing this probability to the odds. So 25% chance. There are two methods that you can look at this. Let's go start method one. Is the horse, it's kind of, so horse is 25%. And so that's its true, we're going to call that its true probability. But 7 to 2, what is 7 to 2 as a percentage? So 7 to 2, as if we were to convert it back to a probability, remember that it's failures to successes. So that means we're saying that this horse is going to win 2 out of every 9 races. And that's equal to 22%. So what's happening here is this house believes that the horse, that it's setting its odds according to the horse having a 22% chance of victory. So by setting the odds at 7 to 2, the house is saying that they believe that the horse has a 22% chance of victory because that's what would make it fair. If the horse had a 22% chance of victory, um, then the 7 to 2 would match it perfectly. If they won 2 out of every 9 races, then these odds would work out perfectly. But because the horse is a 25% chance, according to our figures, that's higher than what the house is saying. So 25% is greater than 22%. So we win more often than the house believes. And so let's do the math to show this. So we win. So let's make a chart. 4 races. We're going to, because it's 25%, we're going to run 4 races. 25% is 1 over 4. So in 4 races, we'll simulate 4 races. And in those 4 races, this horse will win 1 and lose 3. Now, according to the bet sheets, right, we're going to win $7. If we win, we gain $7. And if we lose $2. So total, for that 1 win, we gain $7. For those 3 losses, we lose $6. The net result is we gain $1. So what does that mean? That means that this bet is fair. And not only is it fair, it's more than fair. It's in our favor. This means that on average, assuming the 25% to be true, which our research shows, then we believe that this is a good bet to make. So this bet is slightly in our favor, by 1. So worth to make. That's method number 1. We show the math and we calculate a simulation based on this probability. You could do, essentially turn that to a fraction and then, run that many races. So I did 4 races. You could do, 100 races, whatever, depending on that fraction. That's method 1. Method number 2 is to look at this logically, right? You really don't even need this part because this says that the house is going to, that we're saying that the horse wins more often than the house thinks. And that means we win more often than the house thinks. That tips it in our favor. So method number two kind of uses that. It kind of does it the other way. And so um, instead of turning this into a probability, we could take the horse and turn that into odds. So the house odds seven to two, right? So the true odds, 25%, is equal to 1/4. And what is 1/4 in odds? It's going to be, well, we kind of did it up here, right? 3 fails to 1 win. So how does 3 to 1 compare to 7 to 2? So let's take this and now let's match the denominators. So they're going to lose 3 to win 1. But I'm going to turn this to 6 to 2 to match this. Or you could also turn this to 3.5 to 1. Either way works. But the key is to match the number of wins. Okay, 6 to 2, 7 to 2. And now let's look at what's happening here. The horse is going to the horse is at 62 odds. So what that means is it's going to fail 6 times and win 2. But for those wins, look how much it's paying you. It's paying you 7. That 7 is higher than the fail rate, which means that in order to counteract your fails, you're getting paid extra, more than enough to compensate for your failures. So since 3.5 is greater than 3, or 7 is greater than 6, either way works regardless of what numbers you used. House pays you more than is fair. Therefore, make the bet. So either method works. Whether you turn it into house odds or turn both into odds, or whether you turn both into probability. Um, Either way works, and both are perfectly legitimate ways. And then also, if you want to do the table, I guess that's really kind of the third method, if you will. So I guess there's really 3 different things going on here. You can either use this logic, you can do it with math, or you can use this logic. Either way works, okay? So that's a little bit about how that's work. And so I guess the last thing I'll say is, how would you tell if something's unfair? Well, it's unfair if the amount for the house odds is smaller. So go back to um, this here. Remember, um, this is unfair because when you look at the odds straight out, 37 to 1 versus 35 to 1 for that roulette bet that we did, um, the payout is smaller than what is needed to counteract your losses. You're getting paid $35, but it can't counteract 37 losses. You get the idea? So going back to this now, oops, you can see how that happens here. How the house odds, now the amount that is being paid is more than enough to counteract your losses. Either way works, guys. Um, and there you have it. There's a little lesson on house odds and how to think about what is a fair bet versus an unfair bet. Okay. All right. Don't suddenly go out and gambling. I'm not responsible if you lose all your money. Remember that. Gambling is always going to um, necessarily need to be done safely. All right. This is really purely a mathematical lesson. Okay. Good to know the information, I think, for real life. All right, folks. Have fun, and I'll see you in class.